Mars, our planetary neighbour. It's very cold and dry, and its weak gravity only holds a thin atmosphere. As probes started to visit the red planet, we gained a more accurate view of the surface, and scientists began to wonder. Mars had once been much warmer. It had rivers, and in its early years might have sustained life. A succession of new techniques have been deployed trying to unlock the secrets of the red planet. And while our knowledge of the Martian geology, its atmosphere and its weather has grown immensely, each new mission to Mars raises more questions than it answers. We still don't know if Mars has, at some time, been a home to life. In 1877, astronomer Giovanni Schiaparelli made what he thought was the most accurate map of Mars yet drawn. On it, he showed canals. In the early 20th century, American astronomer Percival Lowell was convinced the canals were signs of a civilization existing on the red planet. So began the search for life on Mars. In 1962, the Soviet Union sent the first probe, the Mars M1, on a flyby mission. It was an audacious project, and it failed. The first of many failures by both the Soviet Union and the United States. Cold War rivalry provided the motivation for these early missions. In 1971, NASA sent Mariner 9 to Mars. It was the first probe to orbit another planet, but scientists discovered that Mars was enveloped in a planetary dust storm. On-orbit photography revealed little more than a red cloud. Soon, Mariner 9 was joined by two Soviet orbiters, both equipped with landers. The Mars 2 lander crashed, but the Mars 3 lander made it to the surface intact. It returned one garbled image and then stopped functioning. Mars now had 3 orbiting spacecraft, all looking at a dusty, featureless planet. The two Soviet probes were identical, but the American probe had one key design difference. While the Soviet orbiters began photographing the planet following predetermined schedules, NASA were able to command Mariner 9 to wait, in hope that the dust would eventually settle. It took months for the atmosphere to clear, but when it did, Mariner 9 saw 3 craters protruding above the dust. They were the tops of giant volcanoes on what was called the Tharsis Plateau. Soon more complex geological features began to emerge. In places, the surface was cratered, suggesting the tectonic forces that constantly renew the Earth's surface were absent on Mars. Volcanic activity that built the solar system's largest volcanoes had stopped billions of years ago. This enabled NASA scientists to compile an accurate global map of Mars and to decide upon landing sites for the Viking probes that followed in 1976. Viking 1 and 2 were identical orbiters, with landers that both made successful landings on the surface. Both returned pictures of the Martian landscape. The primary objective of the Viking program was to find signatures of life. But researchers now feel the 3 experiments tasked with carrying out the analysis had limitations. As researchers on Earth began looking for traces of life in extreme environments, they began to rethink where life on Mars might survive. Yet the consensus at the time was that Mars was sterile, and the idea of life on Mars died. After a 20-year hiatus in Mars research, Mars Global Surveyor went into orbit in 1996. The pictures it relayed back were clearer than anything yet seen from the red planet. Although most Mars orbiters had been tasked with mapping the planet's surface, this was different. The high-resolution images that the Mars Global Surveyor sent back revealed rivers and even river deltas, but the occasional impact crater suggested that nothing has flowed in these systems for billions of years. In July 1997, another probe arrived. The Mars Pathfinder was one of a new breed of missions being pushed by NASA's new administrator under the guiding philosophy of faster, better, cheaper. The idea was to cut development times, cut budgets, and although the risk of failure would rise, the reduced price tag could mean more missions. Pathfinder would land a small rover on the surface. To do this, it used radically new airbag technology. The technique drew more from automotive safety systems than from previous space missions. The landing site, in Mars' northern hemisphere known as Ares Vallis, is one of the planet's rockiest areas. Yet it was thought to be a safe area to land. The broad array of different rock types are believed to have been deposited during an ancient flood. The new landing technique worked perfectly and served as a proof of concept that would be used on future missions. Pathfinder consisted of a base station equipped with 3 solar panels that unfolded like petals. There were sensors to measure atmospheric pressure, air temperature, and wind speed, as well as a transmitter to communicate with Earth. In addition, Pathfinder acted as a base station for the Sojourner rover that explored the surrounding area. Sojourner was fitted with cameras and an alpha particle X-ray spectrometer. It was the first mission to have its own website. The rover returned thousands of images and important detail about the atmosphere and geology, and its popularity guaranteed more Mars missions. On the morning of April 7, 2001, another Mars orbiter was launched. Mars Odyssey was equipped with 3 primary instruments, and it had the ability to act as a relay satellite between future surface missions to the Red Planet and Earth. On its arrival at Mars, it used a new technique to go into orbit. After firing a relatively brief pulse of its engine, Mars Odyssey went into a highly elliptical orbit that, at its closest approach, had it skimming the planet's thin upper atmosphere. Called aerobraking, this technique allowed the craft to circularize its orbit over a period of 3 months, and it saved around 200 kilograms of fuel. The probe is still in operation today, breaking all records as the longest-serving Mars mission. In December 2003, a new player arrived at Mars. The European Space Agency, using a Russian launcher, had sent Mars Express, its first planetary explorer. It was equipped with a lander known as Beagle. Though all contact was lost with the lander, Mars Express continues to return valuable data. The mission has been granted several extensions, the latest till 2020. Equipped with a high-resolution stereo camera, the probe returned unique 3D views of the planet's surface. The orbiter determined that the polar ice caps contain a blend of frozen CO2 and water ice. In the atmosphere, Mars Express detected first methane and then ammonia. Both gases deteriorate rapidly in sunlight, so there must be sources on Mars continually producing them. Methane and ammonia can rarely be made inorganically, but they're generally associated with life. 1 month after Mars Express went into orbit, a NASA lander arrived at Mars, followed 3 weeks later by a second identical craft. They were the Mars exploration rovers called Spirit and Opportunity. Spirit, the first to land, was targeted at the Gusev crater. Opportunity would land at the Meridiani planum on the opposite side of Mars. Though they were much heavier than their Pathfinder predecessor, they used the same bounce landing technique. Both landings were successful and on target. After the craft had righted itself, it detached from the lander and began autonomously unfolding its solar panels and camera mast. While this was happening, the team back at the Jet Propulsion Laboratory waited. Signals confirming the craft's safe arrival took 15 minutes to travel back to Earth. Many of these people had invested years of their lives in this project, and the real mission had only just commenced. Both rovers were designed to operate for 90 Mars days. A solar day on Mars is about 40 minutes longer than an Earth day. And to avoid confusion, the science team operating the rovers refer to a Martian day as a sol. Mission designers, knowing about the dust storms on Mars, felt that the solar panels on the two rovers would eventually be blocked with dirt and stop functioning. But it became clear that the winds on Mars were clearing the panels. Soon, NASA announced that Opportunity had found evidence confirming liquid water had once flowed on Mars. There were pictures from the Meridiani planum of stratified patterns in the rock suggesting sedimentation. The distribution of chlorine and bromine at the site were clues to the areas past as the shore of a salty sea. In April 2004, NASA announced it would extend the rover's missions from 3 to 8 months. It would be the first of many such mission extensions. The rovers were equipped with an abrasion tool to grind away a portion of a rock's surface for a more detailed, uncontaminated analysis of geological samples. This was first done by Spirit at a rock named Adirondack at Gusev crater. It was a first in planetary geology. Researchers agonized before using the tool because of the drain it makes on the rover's energy budget. The rock was made of olivine, pyroxene, and magnetite, making it very similar to volcanic basalt on Earth. When Spirit's right front wheel stopped working, engineers used a duplicate rover to devise a reversing technique that enabled the rover to drag its frozen wheel. This left a furrow behind in the soil, which presented a new area of research for the science team. White or yellow deposits seen within the furrow were various types of salts that only form in the presence of hot water. On Earth, hot water provides an environment in which microbes can thrive. Spirit limped on for another 3 years before it became stuck in loose sand. Again, the engineers began working with a replica which they placed in an identical situation. When nothing was able to free the rover, it was declared a stationary research platform. Further attempts were made to position the rover so its solar panels could operate more effectively, but even this was not possible. The last communication from Spirit was in March 2010. Opportunity lasted until June 2018, when dust clogged its solar panels. In March 2006, NASA's Mars Reconnaissance Orbiter arrived at Mars and began the now routine business of aerobraking. Though this procedure took roughly 6 months, the saving in fuel will see the craft functioning at Mars into the 2030s. One of the primary functions of the new orbiter is as a communications relay station. Its 3-meter antenna transmitting in the ultra-high frequency band enables very high data rates. By November 2013, it had tripled the amount of data sent to Earth by all the other NASA missions combined. Its high-resolution camera began revealing the surface of Mars in the finest detail. These are active falling dunes in East Coprates Chasma. The polar region, free of the seasonal dry ice, again surrounded by dunes. In the southern hemisphere, pits in the residual cap of carbon dioxide. The poles of Mars were now attracting keen interest. Follow the water had become NASA's catch cry. The Phoenix lander was targeted at the northern polar region to follow up on information from Mars Odyssey suggesting frozen water lay beneath the surface near the poles. Because imaging had revealed the region to be unvarying, a rover was deemed unnecessary. The lander had been designed to use a parachute to decelerate, with rocket thrusters to deliver the craft to the surface, unlike NASA's previous 3 rovers, which had bounced. This decision proved controversial, as one strand of research suggested the rocket fuel would contaminate the very area that the lander was tasked with analyzing. The craft waited 15 minutes to allow any dust to settle before it deployed its solar panels. Phoenix had landed during the early spring in Mars's northern hemisphere, so the solar panels would receive plenty of light for the planned 90-day mission. As well as its camera mast, Phoenix was equipped with a meteorological station that recorded the daily weather. It featured a wind indicator and pressure and temperature sensors. In addition, a vertically pointed LiDAR was able to observe cirrus clouds forming in the region and snow falling in the polar atmosphere. These phenomena had not been observed before. The lander also had a robotic arm that could dig half a meter into the soil and deliver samples to the analyzer, a combination of 8 high-temperature ovens and a mass spectrometer. In one excavation, the cameras recorded a white substance which gradually disappeared. Given the temperatures and the time it lasted, it could only have been water ice that sublimated after it was exposed. The soil was slightly alkaline, and the presence of perchlorate, which kills bacteria, was not good news for those hoping for Martian life. Phoenix operated for 2 months longer than planned before the gathering winter completely shaded its solar panels. While the planet still had subterranean deposits of ice, there was precious little left at the surface, yet it was now understood that many of the red planet's features had been carved by running water. Samples analyzed from across the planet affirmed that water and nothing else had made these changes to the Martian landscape. Mars had once been more like Earth, yet it had lost its surface water and most of its atmosphere, and the question of life persisted. Could it have emerged in a warmer, wetter past? And could it still be present below the surface? The next Mars mission would be NASA's most ambitious yet. Known as Curiosity, the car-sized rover would be powered by a nuclear battery, making it immune to the dust problems experienced by Spirit and Opportunity.
7, 6.
Curiosity was launched on an Atlas V from Cape Canaveral in November 2011.
1. Main engine start. 0. And liftoff.
In mid-2012, it entered the Martian atmosphere heading for Gale Crater. The Jet Propulsion Laboratory monitored the entry closely, but had no control over events. In Mars's thin atmosphere, the parachute could only slow the heavy craft to around 320 kilometers per hour. Nearing the surface, the rover descent stage dropped out of the aeroshell and rockets kicked in. At this stage, radar was guiding the lander to the surface, and a small camera was recording images of the terrain below the rover. Next, Curiosity was lowered on a tether beneath the descent stage. This sky crane technique was used to avoid too much swirling dust exposing the rover to unnecessary danger. Everything had worked exactly as it was supposed to, and the American engineers were relieved. The landing had been the most precise ever. Before Curiosity could start work, its computer went through a checklist to make certain that all systems were operating correctly. It was a day before the rover deployed its camera mast and communications antennas. It's thought that Gale Crater is 3.5 billion years old, and that its sediments have been laid down first by water and then by wind. NASA now has a sophisticated mobile science laboratory on Mars, connected to Earth by the most advanced communications link, courtesy of the Mars Reconnaissance Orbiter. The rover's primary objective is to discover if conditions suitable for life ever existed or still exist on Mars. It's also gathering detailed information about the current conditions on the red planet, particularly the radiation levels that will have an impact on proposed manned missions. Curiosity has analyzed the dust from a number of holes it drilled, revealing sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon, all elements essential to life. In its 6 years on the surface of Mars, Curiosity has traveled around 20 kilometers, but the driving is taking its toll. It routinely sends back a series of self-portraits, mainly for diagnostic reasons. Its wheels have taken severe damage, which will undoubtedly lead to design changes for future rovers. Its computers are also giving problems, but a new suite of missions is slated to arrive at Mars in 2020 that will continue profiling the planet. There is one aspect of the Martian environment that has never been investigated, but that's about to be addressed. The Mars InSight probe has been targeted at the flat Elysium Planitia, close to the equator, to spend 2 years investigating the planet's interior. It made a flawless landing in November 2018. After unfurling its solar array, it spent weeks selecting a suitable spot to deploy a seismometer onto the surface to monitor Marsquakes. It's clear that Mars had a warm, wet past, but it's cold and very dry now. Learning about the planet's geological activity will help us know why Mars has changed. The InSight probe also hammered a thermal sensor into the surface to gather data on heat flow from the planet's core. By understanding processes within Mars, we can learn how the geological histories of Mars and Earth began to diverge. The ringed planet Saturn. More than 100 times the mass of Earth, its metallic core lies beneath 80,000 kilometers of liquid hydrogen and helium. It's called a gas giant. Saturn is orbited by at least 62 moons, each unique, some with complex and dynamic environments. Our only detailed examination of the Saturnian system ended in 2017, when the Cassini probe was intentionally crashed into the planet's dense atmosphere to guard against accidental contamination of the moons. Viewed from Earth, Saturn's rings are visible, but not in any detail. They were thought to be solid, until mathematical analysis suggested they were orbiting particles. But how did they get there? And why was Saturn alone in having rings? In the early days of space research, Saturn was just too far away. Conventional rockets could only just reach Mars. In 1964, NASA realized that a space probe launched in 1977 could take advantage of a rare alignment of the outer planets to fly past all the gas giants. Using gravitational assistance from the planets, it would just be possible with the technology of the day. An ambitious new mission began to take shape. It was dubbed the Grand Tour. Two probes that were far in advance of anything yet attempted would be part of the Mariner series. Because no spacecraft had been sent beyond Mars, mission planners felt it would be wise to send two rudimentary advanced probes to Jupiter and Saturn to test the deep space environment. Researchers didn't know if it was even possible to cross the asteroid belt between Mars and Jupiter. In 1972, Pioneer 10 was launched towards Jupiter, and the following year, a twin, Pioneer 11, was sent to Saturn. Both craft passed by Jupiter and discovered that the electron radiation there was 10,000 times as strong as at Earth. This was a surprise to engineers at NASA, who had to modify the more sophisticated craft they were preparing for the Grand Tour. The probes, being built at NASA's Jet Propulsion Laboratory, were part of a program known as Mariner Jupiter-Saturn, but this was soon changed to the Voyager program. They were launched 16 days apart in late 1977, while Pioneer 10 was heading toward interstellar space, and Pioneer 11 was still 2 years away from Saturn. In 1979, as Pioneer 11 approached the ringed planet, it began sending back pictures far clearer than anything seen before. A new ring, the F ring, was observed for the first time. The craft flew by Saturn, passing beneath the rings. Mission planners were uncertain how broadly the ring particles spread. If there was a threat to the spacecraft, They were prepared to sacrifice Pioneer 11 to get a clear idea of the environment they would encounter with the following Voyager craft. The probe passed the rings safely and continued beyond Saturn into interstellar space. NASA received its last communication from the probe on the 24th of November 1995. The following Voyager 1 and 2 probes were very robust, designed to survive for a very long journey and with far greater technical capacity than the Pioneers. In late 1980, Voyager 1 approached Saturn. Although its high-resolution polarimeter had failed, it was still able to see a new ring called the G ring, orbiting 100,000 kilometers above Saturn's cloud tops. For the first time, researchers could see how the rings moved. Uneven features within the rings were called spokes. They're transient and are thought to be particles lifted by an electrostatic charge. After such a long preparation, information was now coming into JPL at such a rapid rate that the planetary scientists were overwhelmed. Saturn's moons were of great interest. Voyager 1's path had been chosen because it would take it close to Titan, the solar system's second largest moon, and the only one to hold an atmosphere. But the images were disappointing because the thick atmosphere of methane and nitrogen was impenetrable. Voyager 1 now looped up above the solar system on a trajectory that would take it to interstellar space. As it looked back at Saturn, it captured one last image from a unique angle. It was almost 10 months before Voyager 2 neared Saturn. Its different path meant that it could continue on to Uranus and then to Neptune. Its high-definition camera was still working, and planetary researchers were expecting detailed pictures of the rings. They were not disappointed. The varying densities and spacing within the rings was more complex than anyone had expected. The rings are named for letters of the alphabet in the order that they were discovered. It became apparent that the rings had changed in the time since Voyager 1 had seen them. Though they stretch from 7,000 to 80,000 kilometers above Saturn's equator, their thickness is on average just 30 meters. The spacecraft also returned pictures of the moon Enceladus. Its cracked, uncratered surface was made of ice, below which is an ocean. Ultimately, Voyager 2 left Saturn. Unable to go into orbit, it sped on toward Uranus. It would be 23 years before another probe visited.
And liftoff of the Cassini spacecraft on a 30-mile trek to Saturn.
Launched in 1997, Cassini was a collaboration between NASA, the European Space Agency, and the Italian Space Agency. It would take more than 6 years to reach Saturn. Cassini was the biggest, most complex interplanetary spacecraft yet devised. Its 12 different instruments each had a dedicated team of research specialists on Earth to interpret the data it sent back. Its high-gain antenna was used for high-speed data relay back to Earth, but in what's called a ram maneuver, it was sometimes used as a shield to protect the spacecraft from debris impact, especially when crossing the plane of Saturn's rings. On the 1st of July 2004, it fired its engine to go into orbit around Saturn. It was designed not to fail. Beside its main engine was a backup in case the primary engine did fail. It had 16 monopropellant thrusters, 8 prime and 8 more, also as backups. In mission control at the Jet Propulsion Laboratory, the engineers could not know what was going on. The time delay and Cassini's disappearance behind Saturn meant that much of the telemetry was recorded for later replay back to Earth. The engine burn lasted for 106 minutes. Cassini was the first probe to employ a solid-state recorder, unlike the earlier Voyager craft that registered data on a mechanical tape recorder. Cassini's first orbit followed a highly elliptical path that would take it out past the moon Titan. This was important for two reasons. Its gravity would be necessary in modifying Cassini's course, so Saturn and its other moons could be observed from different perspectives. Secondly, Titan, with its dense atmosphere, was targeted as an area of major interest for the Cassini team. The European Space Agency had built a small craft called Huygens, attached to the side of Cassini. On its second approach to Titan, the Huygens probe was released. It was equipped with a heat shield, a parachute, and enough battery power to last for several weeks. Over a 20-day period, Huygens drifted for 4 million kilometers. It would transmit data back to the orbiting Cassini, which would later relay it to Earth. 3 days after separation, Cassini made a course correction that would prevent it colliding with Titan. As Huygens reached Titan's atmosphere, Cassini was coming around for its third close approach of the Moon, ready to receive signals from the lander. While it drifted to the surface of Titan, Huygens sampled the atmosphere and recorded images of the landscape. Pictures from beneath the clouds revealed low hills and channels cut by flowing liquid. There were few impact craters, and those that existed were heavily eroded. It was the first landing on a body in the outer solar system. Images from the surface showed weathered rocks made of water ice. What surprised everybody was that Titan is a geologically active world, where liquid ethane and methane, rather than water, have carved the features. As Cassini continued looping out around Titan, it used radar to map the Moon's surface, confirming the widespread distribution of hydrocarbon lakes. The probe discovered that rain fell on Titan, but it was a mixture of liquid ethane and methane. The Moon has weather and other erosive forces similar to Earth, but the chemistry is radically different. The small moon Enceladus drew attention to itself as the whitest, most reflective body in the solar system. Its surface shows cratering in the north, but the south has giant cracks known as tiger stripes. On Cassini's first loop past Enceladus, the magnetometer team noticed an odd deflection of Saturn's magnetic field, as though the small moon had an atmosphere. During its second pass, the team noticed the same phenomenon. They asked for the next traverse of Enceladus to pass much closer, so Cassini's course was modified to fly just 175 kilometers above the icy moon. The probe passed through a plume of water vapor emanating from the tiger stripes. It contained common salt. In all, Cassini made 24 swoops past Enceladus, with the closest approach flying just 25 kilometers above the surface. Each one of the probe's instruments gathered different evidence about the jets of water expelled through the cracks in the moon's south. On Mars, rovers have been combing the surface looking for traces of life, but Enceladus was flaunting remarkable signs. Gravitational analysis revealed a liquid ocean beneath the ice, and infrared detectors saw heat emanating from the cracks. As well as salt, the science team discovered traces of silica that can only dissolve in hot water. Hydrogen and organic compounds were also detected.
We know from Cassini that Enceladus has a global ocean, so you have water. We also know that there are organics coming out because they've been directly measured, both in the gas and in the particles. We also know there's a source of energy. The South Pole was hotter than the rest of Enceladus. And then we found evidence that deep inside, there are hydrothermal vents on the seafloor of Enceladus. So these hydrothermal vents would supply the heat and the nutrients that could possibly support life.
With a diameter of 500 kilometers, Enceladus is just too small to sustain a hot core via radioactive decay. Gravitational squeezing by Saturn explains some of the heating, but the source of the high temperatures detected remains a mystery.
But not only is there liquid water underneath the surface, but there's organic material, there's a heat source. And you know, when people get excited about the potential for life elsewhere in the solar system, there are four things that you need. You need a heat source, you need liquid water, you need organic material, and you need those three things to be stable over some period of time so that life could potentially form. At Enceladus, we've got three. We're not sure about the stability over time yet.
In the Earth's deep oceans, hydrothermal vents provide the warmth and nutrition to support life. They may even have been important for the origins of life. Planetary biologists are speculating that the environment in the oceans of Enceladus may be the most likely place in the solar system to find some sort of extraterrestrial life. It took a while for Cassini to be in a position where backlighting from the sun allowed the imaging team to capture pictures of the plumes. Using a similar technique, the imaging team took this picture with Saturn directly between Cassini and the Sun. It reveals Saturn's E-ring, the hazy outermost ring that is usually very difficult to see. The E-ring is a result of the plumes from Enceladus and is constantly replenished by the saltwater eruptions. Saying that Saturn has 62 moons is misleading. Each particle within the ring system could be regarded as a moon. There are the inner large moons and the outer large moons. There are the shepherds that shape the rings. There are co-orbitals that exchange orbits. And there are even moons that orbit other moons. All are unique. During the Voyager missions, interest in the moons came as something of an afterthought. But for Cassini, close examination of the moons was planned from the beginning. Iapetus orbits Saturn beyond Titan. It was first observed in 1671 by Giovanni Cassini. He could see it as a dot of light to the west of Saturn, but could not see it when it should have been to the east. Iapetus has one bright face and one dark one. Because the moon is tidally locked to Saturn, it is always the dark face that leads as it orbits. One theory suggests that it sweeps up debris that spews from Phoebe, a more distant moon. Another feature of Iapetus has scientists baffled. A ridge along the equator stretches more than halfway around the moon. It's twice as high as Earth's tallest mountain. With Iapetus being just 1,500 kilometers across, the ridge gives Iapetus the appearance of a walnut. very accurately directed bursts from Cassini's main engine allowed mission engineers to modify the probe's looping orbits so mission specialists could focus on various moons, different areas of the ring system, or different parts of Saturn itself. With gravitational assistance from the moons, particularly Titan, mission control were able to conserve fuel. The Cassini probe performed so well it received 2 mission extensions, but the fuel could not last forever. Planners had scheduled the most hazardous part of Cassini's mission for its final year at Saturn. Late in 2016, Cassini began a series of polar orbits that would take it close to the outer edge of the rings. In what mission specialists called grazing on the rings, the craft's mass spectrometer and its cosmic dust analyzer would sample particles and gases as it crossed the ring plane. In orbit 251, its first pass above Saturn's North Pole, it recorded the peculiar hexagonal storm that was first hinted at by the Voyagers. The storm, more than twice the diameter of Earth, maintains its hexagonal shape, but its color changed with the advance of summer. At its center is a cyclone, shown here in false color, with red indicating lower cloud and green higher cloud. Winds at its edge blow at 540 kilometers per hour. One part of Cassini's dual technique magnetometer had stopped working early in the mission. Without it, the craft had to do roll maneuvers from time to time to calibrate the instrument. The spacecraft would make 20 ring-grazing orbits, with the work of its instruments mapped out to the second. As the Sun was almost directly behind the rings, Cassini looked for dust clouds. Something is reducing ring particles to fine powder. Cassini made a number of radio occultation observations. With the rings between the spacecraft and Earth, 3 radio signals of differing wavelengths were transmitted simultaneously, allowing the radio science team to build a profile of the ring particles. This false color image of the A ring, the outermost of the large bright rings, shows red for particles larger than 5 centimeters across. Green denotes particles smaller than 5 centimeters, with blue for particles smaller than 1 centimeter. The complex gravitational interaction between Saturn, its rings, and its moons leads to gaps in very particular places. Before Cassini arrived, only 18 moons were known. That number has grown to 62. Prometheus acts as a shepherding moon, limiting the inner edge of Saturn's F ring. Along with Pandora, which orbits outside the F ring, the 2 moons keep the ring narrowly confined. In April 2017, Cassini's orbit was changed for the final phase of its mission. The probe would now loop inside the rings. Though it would ultimately mean burning up in Saturn's atmosphere, the information gathered from such close proximity to Saturn and its rings would give a fuller picture of the gas giant. It was decided that intentionally destroying Cassini was preferable to letting it drift without fuel, possibly contaminating one of the moons. Cassini's sensors began picking up a stream of ring particles raining down upon Saturn. A continuous shower of ice and dust particles are dragged toward the planet's equator by gravity, or at higher latitudes, charged ring particles spiral in along magnetic field lines. Every second, 10,000 kilograms of ring rain falls to the surface. At this rate, the rings will be completely gone in 100 million years. Researchers were surprised to discover an electric current flowing between the inner D ring and the upper atmosphere. Toward the end of Cassini's close passes of Saturn, the spacecraft began catching the upper edge of the atmosphere. information had been retrieved from the recorders. Data now was transmitted directly back to Earth, but it relied on the spacecraft's thrusters to stop Cassini from tumbling, keeping its high-gain antenna pointed accurately. The probe's final work was sampling the atmosphere and measuring the offset of Saturn's magnetic axis.
This is PCS-1. We just had transition to high rate mode.
In mission control, there was no more control. The engineers could just monitor the signals sent from Saturn 84 minutes previously.
The signal from the spacecraft is gone, and within the next 45 seconds, so will be the spacecraft.
It will take years to process the data gained from Cassini. As yet, there are no future missions to Saturn scheduled. Jupiter is our solar system's largest planet. It's more than twice the mass of all the other planets combined. Its swirling atmosphere moves in bands at different latitudes, and its great red spot is thought to be a perpetual storm. Recently, images from a new probe that has flown above Jupiter's poles reveal a completely different planet. The ancient Romans knew Jupiter as the celestial representation of the king of the gods. In 1610, Galileo, using his newly improved telescope, saw Jupiter's moons and could see they orbited the planet, evidence that not everything revolved around the Earth as the Church had declared. Though better telescopes improved our view of Jupiter, it was not until 1964 that Gary Flandreau, a graduate student working part-time at NASA's JPL, understood there was a way to get a clearer look at Jupiter. By plotting the positions of the outer planets, he realized that a rare alignment would enable a spacecraft, launched in 1977, to visit Jupiter, Saturn, Uranus, and Neptune. NASA jumped at the opportunity and began work on twin craft for what was then known as the Planetary Grand Tour. To limit any surprises, two basic spacecraft, known as Pioneer 10 and 11, were quickly built. They would go ahead of the Grand Tour missions to send back information about the environment. Pioneer 10 was launched toward Jupiter in March 1972. It was the first spacecraft to cross the asteroid belt that lay between Mars and Jupiter, and because it was the first probe on a trajectory that would take it out of the solar system, it carried a plaque identifying its origin. By December 1973, Pioneer 10 was sending back pictures of Jupiter clearer than anything that had been seen before. Approaching Jupiter, it encountered levels of ion radiation 10,000 times more intense than the radiation belts surrounding Earth. As the probe skimmed past the giant planet, it gained speed. Leaving Earth, Pioneer 10 was moving at 51,000 kilometers per hour. Departing Jupiter, it had more than doubled its speed. This gravitational slingshot effect made the Grand Tour possible. The Grand Tour craft, recently renamed Voyager 1 and 2, were due to be transferred to Cape Canaveral for launch integration when news of Jupiter's extreme radiation environment came through. The electron radiation at Jupiter had generated false commands within Pioneer 10. With the far more sophisticated Voyagers, this presented problems. Local supermarkets were stripped of their stocks of kitchen-grade aluminium foil, which was then used to shield critical cables. Without this last-minute alteration, electrical pressures of up to 40,000 volts would have been induced in the Voyager's subsystems as the craft passed Jupiter. Voyager 2 was launched in August 1977. Its trajectory meant that it could visit Jupiter, Saturn, Uranus, and Neptune.
To extend man's senses farther into the solar system than ever.
Voyager 1 left 16 days later. Its different, faster trajectory only allowed flybys of Jupiter and Saturn and various large moons. At the time, the Voyager spacecraft were the most sophisticated probes to be launched. Because they were to operate at huge distances from the Sun, solar panels could not be used as a power source. They were equipped with radioisotope thermoelectric generators which use the heat from the decay of plutonium-238 to generate power. As Voyager 1 approached Jupiter in January 1979, it began sending image sequences that showed a complex and dynamic planet. The planet's giant red spot was revealed as a vast rotating storm. In 1665, Giovanni Cassini described a permanent spot on Jupiter which was regularly observed into the 1700s. It was not until the late 1800s that Jupiter's spot was described as red, and it's uncertain whether the historic observations of Jupiter's spot refer to the same feature or a phenomenon that regularly manifests in Jupiter's atmosphere. Voyager 1 made its closest approach early in March 1979. As the probe neared Jupiter, the activity at NASA's Jet Propulsion Laboratory became intense. This was the nature of the Voyager's flyby missions. There were long, quiet cruise phases between the planets, followed by brief periods when the flow of information from the craft overwhelmed researchers. One of the biggest contributions made by the Voyagers was the transformation in our understanding of the Galilean moons. Previously just dots of light, Jupiter's 4 largest moons were each distinct and completely different. The first surprise was the inner moon Io. It's a sulfurous yellow in appearance, and one particular long-duration exposure revealed an odd plume. Rather than being a cold, dead world, the gravitational squeezing Io receives from its giant neighbour heats the moon's interior. The plume was a volcanic eruption, ejecting material hundreds of kilometers above the surface. In July 1979, 3 months after Voyager 1 had moved beyond Jupiter, Voyager 2 made its closest approach. It was able to examine different moons more closely than its twin. Europa was the next surprise. It is highly reflective and has the smoothest surface of any body in the solar system. Further observation revealed pressure ridges reminiscent of polar ice flows on Earth. Europa is a frozen world, with a vast ocean beneath a thick crust of ice. Like Io, it is heated from within by tidal flexing. As Voyager 2 continued towards Saturn, planetary researchers were left with large amounts of raw data about Jupiter still to be processed. The Voyager missions left us with a basic view of the Jovian system, but they had raised more questions than they were able to answer. It would be more than 10 years before Jupiter received another visitor from Earth.
Ignition and liftoff of Discovery and the Ulysses spacecraft bound for the polar regions of the Sun.
In October 1990, the Space Shuttle Discovery lifted the European Ulysses spacecraft to low Earth orbit. From there, it was boosted on a mission to observe the Sun, but first, it would pass Jupiter. All the planets orbit the Sun in the same direction, in roughly the same plane. This is called the ecliptic, and it developed from the spinning disk of dust and gas that formed our solar system. The designers of the Ulysses spacecraft wanted to see the Sun from an orbit above its poles. Jupiter's extreme gravitation was used to bend the probe's flight path out of the ecliptic so it could make north-south orbits of the Sun. Ulysses was not the only probe to take advantage of Jupiter's gravity. Both the Cassini probe to Saturn, launched in 1997, and the New Horizons probe to Pluto, launched in 2006, were able to reduce their flight times by years with Jupiter flybys. These probes were able to make meaningful observations while passing the giant planet. In the clean rooms of the Jet Propulsion Laboratory, a new probe was taking shape. Galileo would be the first spacecraft to go into orbit around Jupiter. Its 4.8-meter antenna was folded like an umbrella, only to be deployed when safely on the way to Jupiter. Originally scheduled to launch in 1986, it sat in storage for years after the Space Shuttle Challenger exploded.
10, 9,
It launched aboard Space Shuttle Atlantis in October 1989.
4, 3, 2, 1. We have ignition and liftoff of Atlantis and the Galileo spacecraft bound for Jupiter.
New rules governing shuttle launches meant a change in the booster to push Galileo out of Earth orbit. The less powerful solid fuel upper stage, now stipulated, sent Galileo toward Venus for a gravity assist. The new flight path meant Galileo was traveling to a hotter part of the solar system. It was decided to keep the heat-sensitive antenna furled until after the spacecraft looped back past Earth. Galileo made 2 close passes of Earth, each time gaining more speed. Its first pass was in December 1990, more than a year after its launch. A further year on, when it passed Earth again, the high-gain antenna was only partially open. After months of trying different techniques to deploy the antenna, mission engineers concluded that long periods in storage had caused lubricant at the tips of the antenna's ribs to dissipate. Researchers would rely on Galileo's smaller antenna, with data delivered at slower rates. During the cruise to Jupiter, Galileo encountered several asteroids. This is Ida, the first asteroid we've learnt of with its own moon, Dactyl. In July 1995, while it was still 6 months away from its closest encounter with Jupiter, Galileo ejected a small probe designed to enter the atmosphere and sample its chemical composition. The probe lasted for an hour in Jupiter's atmosphere. The data was relayed to Galileo and recorded for subsequent transmission back to Earth. Its analysis revealed hardly any water vapor, which was unexpected, and other elements, particularly helium, were detected at far lower levels than predicted. The probe experienced areas of extreme heat and cold, suggesting heat is being released from the planet's interior. Slightly more than an hour after transmission from the probe ceased, Galileo began its orbit insertion burn. Its engine had to operate for 49 minutes to put it into a highly elliptical equatorial orbit. But this orbit would be altered with another burn at its high point. Mission designers were acutely aware of the high radiation environment, and the second burn would lift Galileo above the extreme radiation at its closest approach. Galileo's initial orbit eventually delivered a close approach to Ganymede, Jupiter's largest moon. During this orbit, engineers were trying to understand damage to the spacecraft's vital tape recorder. Without its high-gain antenna, the recorder was essential for slow replay of data recorded during the brief, close encounters. It had been stuck in rewind for 15 hours, and tape had been degraded. light-emitting diodes, key elements in the recorder's control system, had acquired radiation defects. The second orbit also passed Ganymede. Galileo discovered it's the only moon in the solar system with a significant magnetic field. It also has an ocean sandwiched between two layers of ice. Galileo's orbits would be slightly varied so that it could make close approaches to different Jovian moons. But the equatorial orbits needed to reach the moons also took the craft through hotspots in Jupiter's radiation belts. With the observations made by the voyagers, the moon Europa was of particular interest to the Galileo team. Data from several instruments agreed that a salty ocean exists beneath Europa's surface ice. Later examination of the Galileo datasets revealed plasma wave and magnetic field information, showing that plumes of water vapor were erupting from cracks in the surface. Europa has more water than Earth, which makes it a possible home to life. Io was already known to have volcanic activity, but Galileo saw tides in the moon's solid surface of more than 100 meters. The temperatures generated by this gravitational distortion of Io make its numerous volcanoes hotter than anything found on Earth. During its 8 years at Jupiter, Galileo completed 35 orbits, filling out our limited picture of the Jovian system. This was never an easy mission. Galileo was a robust spacecraft, but the radiation environment stressed all the subsystems, and engineers were constantly having to find workarounds for the frequent breakdowns Galileo suffered. Instruments showed increased noise when near Jupiter, and current leakages caused by radiation led to several resets of the onboard computer, with crucial loss of data. Software changes enabled the computer to recognize these resets and to recover by itself. Information learned would lead to changes in the way the next Jupiter spacecraft was designed.
5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter.
In August 2011, Juno began a journey to Jupiter that would last almost 5 years. Its mission parameters would be very different to Galileo's. It would ignore the moons and focus exclusively on Jupiter.
Chamber pressures have plateaued.
Spacecraft design saw crucial electronics shielded within a thick titanium vault, and rather than a plutonium power source, Juno would rely on solar panels. The sun's intensity at Jupiter is roughly 5% of what it is at Earth, so the panels are huge. A shortage in stocks of plutonium-238 led to the change in power sources. Juno followed a looping orbit that took it beyond Mars before swooping back to Earth for a gravitational boost that added 14,000 kilometers per hour to its velocity, sending it on to Jupiter. Juno approached Jupiter on a path that took it above the planet's north pole. It was destined for a north-south orbit. This would see it pass beneath the severest sections of the planet's radiation belts that extend out from Jupiter's equator. 4 days before its closest approach, Mission Control sent a command that initiated the craft's autopilot. On July the 4th, 2016, Juno began an engine burn that would insert it into a 53-day orbit. 48 minutes later, Mission Control at JPL received tones verifying that Juno had started its deceleration maneuver. It was a tense 35-minute wait from the system's engineers before confirmation came through that Juno had performed exactly as intended. For the Juno scientists and engineers, it was a relief that things were going to plan. Juno is equipped with a suite of instruments capable of penetrating Jupiter's thick cloud. The polar orbit allows Juno to compile a three-dimensional map of the upper atmosphere, building a picture of the entire planet as it rotates. The images of Jupiter from this new perspective appeared to come from a different planet. Researchers were stunned. It was planned that Juno would only make two 53-day orbits and then change to a series of 14-day orbits that would speed up the sampling rate. The spacecraft's main engine is fueled by hydrazine and nitrogen tetroxide, which ignite spontaneously when mixed. The propellant and oxidizer are forced out by a bladder of expanding helium. As Juno was finishing its second orbit, the helium valves were not responding correctly, so it was decided to maintain the original orbit. A mission extension has been granted to allow for the longer orbits Juno continues to follow. Within a day of the helium valve problem, Juno went into safe mode. All instruments went offline and data was lost. It appeared to be similar to the difficulties experienced by Galileo, but engineers traced the issue to a data transfer problem from one specific instrument, and the spacecraft remains healthy. Jupiter's axis is tilted at only 3 degrees, making even an oblique view of the poles near impossible until Juno arrived. When viewed in the infrared, researchers saw a complex arrangement of storms at both the poles. At the North Pole, a central vortex is surrounded by 8 anticyclones. At the South Pole, 5 anticyclones surround the central storm. Scientists do not understand why the storms, all rotating in the same direction, do not obliterate each other. On its 7th close pass of Jupiter, Juno flew directly over the giant red spot. Its microwave radiometer was able to map the heat distributions at varying levels down to 350 kilometers. The red spot is a giant storm, and Juno was able to see much higher temperatures at the deepest levels they could penetrate. With no geographic features, as on Earth, there is nothing on Jupiter against which storms can dissipate. The Great Red Spot remains firmly 22 degrees below the equator, yet it appears to have drifted around the planet at least 10 times since reliable observations began. Jupiter's magnetosphere is huge. It traps charged particles in bands stretching out to vast distances. This gives sensitive electronics on orbiting spacecraft like Juno big problems. It was assumed that Jupiter's magnetosphere was generated, like Earth's, by dynamo action, the convective movement of an electrically conductive fluid deep within. So far, results from Juno suggest that this is not the case. The lumpy nature of Jupiter's magnetic field points to an atmospheric source. The giant auroras at the poles also seem to come from a different mechanism than here on Earth. By focusing on the composition of the gas giant, researchers are hoping to gather clues about conditions at the formation of the solar system. While the Earth has been continuously changed by tectonic forces, it is thought that Jupiter remains very similar in composition to the cloud of gas and dust from which the solar system was formed. At the end of its mission, Juno will be sent on a collision course with Jupiter to avoid any possible contamination of the delicate moons. The next mission to the Jovian system will focus on Europa, as the most likely place after Earth to harbour some form of life. Known as Europa Clipper, it's scheduled to launch in 2022. Like Juno, it will be solar-powered, and its elliptical orbit of Jupiter will see it fly over Europa every 2 weeks. Early concepts for the mission called for the inclusion of a lander, but this idea was soon rejected as premature because more needs to be learned about the surface of the icy moon. Though Europa's ice crust is thought to be at least 19 kilometers thick, accurate measurements need to be made. If thin areas can be found, then future missions may be able to access the ocean that lies beneath. Concepts for under-ice explorers are in development, and we can expect other missions to focus on other moons. As the largest planet, Jupiter's influence on the rest of the solar system is profound. It has more than twice the mass of every other planet combined. All other planets' orbits are affected by Jupiter's gravitation. There is still much to learn about Jupiter.